This is our 7th such conference, I think, and it's getting, it's very nice to have all of you here and also to have such distinguished outside speakers today. I'm going to talk about some differences that we have seen in terms of performance in adaptive designs for confirmatory trials where there are multiple treatment arms. Now, these different, the methods that were first developed for comparing multi-arm trials were developed by, I think, Peter Bauer and Bauer, then Bauer and Kieser, Bauer and Kuhn, and then, Martin Posch. A lot of the work was done on this p-value combination method, where you have multiple treatment arms, you have an interim analysis, and then you select a few of them, and in the end, you have pairwise comparisons to a common control arm, and the goal there is that you must control the type 1 error in a strong sense, because these trials are intended for regulatory consumption. But group sequential methods, where you also have multiple arms against a common control, are a competitor in a sense, and they have not been used that much because perhaps the computational approach was not so easy. And recently we've investigated this problem because our e-software and a lot of our research came from the group sequential approach. And so this talk is going to compare the two. So I'm going to first introduce the group sequential procedure, and then and here we are talking about adaptive enhancements, which means essentially, sample size re-estimation and dose selection, and then the FWER, the family-wise error rate control for these. I'll quickly talk about the p-value combination approach, which maybe you are more familiar with because that's been around for a long time. And I'll try to compare the two as apples to apples in the sense that we will use the same same test statistic for the two approaches. And then we'll do a head-to-head comparison of the two. And then finally, I'll introduce a actual clinical trial where we use some of these methods. So here's the problem. Now, it's a multi-arm problem. Eventually, we hope to be able to treat this as a multi-group problem for treating multiple populations. But here is multiple treatment arms against a common control arm, and delta is the treatment effect. So there are there are D treatment effects. Each delta is the difference of the mean of the treatment versus the common control. So delta 1 through delta capital D. The null hypothesis is that all of these are ineffective. They're all equal to 0, same as control. And we're talking about one-sided alternatives that at least one of them is greater than 0. And I'm going to restrict this to two-stage designs, one interim analysis, and possible early stopping, and then possible sample size re-estimation at the end of stage 1. At least the group sequential part is directly generalizable to more than 2 stages. So in the group sequential approach, what you do is, you have D of these, the subscript I refers to the treatment, so you have delta I1, so you estimate them, and so the delta hats are the estimates of the deltas at each stage. And so the first subscript refers to the treatment, which I goes from 1 to capital D, and the second subscript refers to the stage. It's a two-stage design, so J equals 1 is the first stage, J equals 2 is the second stage. So you estimate these deltas, and then you estimate their variance, or the Fisher information, and and then you calculate the score. So you have Wij is the score for treatment I at stage J, and then for convenience, I'm writing it as a vector of D scores with a underline below it. And this Wj is a Brownian motion. We can show that it has independent increments across stages. It's independent increments. But within a stage, that's the difference between the usual two-arm group sequential design and the multi-arm, that within a stage, these Ws are all correlated because they're all being compared to a common control. And that correlation is known. You can, it depends on the sample sizes, essentially. So you can find group sequential boundaries. This is just the generalization of the two-arm boundaries, except that you now have to work with the max statistic. So you find the stopping boundaries for the first look and the second look by saying, I'm going to spend alpha 1 at the first look, and then alpha minus alpha 1 at the second look. And so I want to find the boundary B1 such that the maximum of these Ws exceeds B1. That probability under the null hypothesis, under the global null hypothesis, is alpha 1. And then once you have gotten B1, you can find B2 by saying, well, now I want the probability of remaining within the continuation region at the first stage, and then going into the rejection region at the second stage to be alpha minus alpha 1, and so I can find B2. Now, these boundaries are under the global null, but nevertheless, they have strong control of type 1 error because of the fact that you're using the max statistic, and that has been demonstrated in a recent paper by people from Britain, Sue Todd and others. Now, and this we published a way of getting these boundaries for up to K stages in this paper last year. But we are sticking with the two-stage designs. Now, this is classical group sequential, no adaptations. You can adapt by saying, well, at the end of stage 1, I want to select some doses. I don't want to go forward with all of them. And in addition, I want to maybe consolidate the sample sizes. Since I've saved some sample size by dropping ineffective doses, I want to use them for the ones that are going forward. Or I might even increase the sample sizes of the ones going forward. So those are the two adaptations. And now once you do these types of adaptations, you have to adjust the boundaries because now the type 1 error will no longer be preserved. And so to control the family-wise error rate, you'll have to recompute that second stage boundary. First stage boundary, there was no issue. You just stop the trial if you cross the boundary. But now if you didn't cross the boundary at the first stage and you drop arms, then you have to make adjustments. And the adjustments are of two types. One is the adjustment that is due to so-called closed testing that controls multiplicity. And then there's a second adjustment due to work of Mueller and Schaefer for preserving conditional error rate. I'll explain both types of adjustments. So as an illustration, let's take a three-arm case. Three active doses and a control. So now, and they're indexed by 1, 2, and 3. And let's suppose that at the end of stage 1, only doses 2 and 3 go forward. So this S is the set of doses that go forward to the second stage. And let's suppose that the sample size is reallocated to these doses that are going forward after you drop dose 1. So now we are interested at the end of the study in each of them. We want to know whether dose 2 was statistically significantly different from control. And we want to know whether dose 3 was. So we have two hypotheses that we want to test. Now, and we can test them, but let's say we want to test H2. then the closed testing principle requires that to reject H2 with strong control of type 1 error, you must not only reject it by itself with a valid level alpha test, we also reject it in combination with every other treatment that was in the trial that is also intersects with it. So not only must you test that delta 2 is equal to 0, but you must also have a valid test that delta 1 and delta 2 are both equal to 0 with a valid test, or delta 2 and delta 3 are both equal to 0, and finally the intersection of all three, delta 1, delta 2. So there are three additional hurdles in addition to the hurdle of simply testing delta 2 by itself. And similarly, if you want to reject H3, you'll have to test it in intersection with all the other treatments that include it. So that's so therefore, it pays us to think more generally and say let's just test HI, where I is one of these elements. Either it's this 2 by itself, or 1 and 2, or 2 and 3, or 1, 2, and 3. How do you test HI with strong control of type 1 error? So there are two steps. The first step is, let's say you were testing I is 2 and 3. Then the first thing is you don't need the boundaries that you had the first time. The boundaries that you had the first time, B1 and B2, those boundaries were good for 3 active doses. So they are really very high. Now, if you're only testing 2 active doses, you can get more generous boundaries, boundaries that are slightly lower. So you can recompute, just like you computed for the 3 active dose case, you can compute for the 2 active dose case and calculate BI1 such that the max, now this W only has 2 doses in it, so you'll have a lower boundary, but you'll still be spending alpha 1. And then, you can find BI2, where again in the same manner, the probability of staying in the continuation region for the first look and going to the rejection region at the second look. And so for instance, if it was if there were 3 doses in here, then these boundaries would have been much higher, much more strict. With only 2 doses, they'll be even less strict. And if I is just 1 dose and a control, then it'll be the usual Lan and Demetz boundaries that you would get from East for the 2-arm case. So that's one thing you do right away to improve things. But you can do one more thing to further improve these boundaries. So at the first look, of course, if you cross, if the observed maximum statistic exceeds BI1, then automatically HI is rejected. But if otherwise, you can further readjust the second look boundary by the conditional error rate method. So here is the conditional error rate is an idea of Mueller and Schaefer, which says that if you want to preserve the overall type 1 error of a test, then what you need to do, of an adaptive test, then what you need to do is preserve the conditional type 1 error. That is, the conditional type 1 error, if you made no change to the design, would be this right-hand side, the probability that the max of WI2 is greater than its boundary. And then the left-hand side is the probability if you made a selection. So if you drop doses, for instance, then the left-hand side is the conditional error after you made the adaptive change. Either you drop doses, or you increase sample size, or you did both. And the right-hand side is if you didn't make that adaptive change. And it's conditional on what you saw at stage 1. So you can find the boundary such that this conditional error is preserved. That the conditional type 1 error under the null hypothesis, if you made a change, should not exceed the conditional type 1 error if you made no change. So now you have a new boundary, and you will reject the null hypothesis if the observed max exceeds this new boundary. And that will preserve the type 1 error. Now you have to do this for every single I in this set, so that you manage the closed testing principle. So that's how the group sequential method can be extended to adaptive. Now the combination p-value method is much simpler. There's no you only have to worry about closed testing. You don't preserve the conditional type 1 error. And what you do, again, let's recall that there are 3 active doses, and 2 of them are going forward, and you want to, and then I is all possible intersections. If you want to test H2, then you want to test it by itself with dose 1, with dose 3, and with doses 1, 2, and 3. Then the p-value combination is you calculate the p-value for the first stage, and you calculate a p-value for the second stage, and then you combine them with different combination functions. The one that sort of used the most is the so-called inverse normal combination function. So you take, now you have considerable flexibility for how you get those p-values for the 2 stages. You can use some of these non-parametric methods like Bonferroni or Symes, or you can use, since we are trying to compare the p-value combination method with the group sequential, we should use the p-value that's equivalent to the test for the group sequential, which in this case is the Dunitz p-value, which is based on the max of the W's. So, so we would use this max statistic to get the p-values, and to be more specific, what you do is the first stage p-value would be the probability that the max of the WI1s is greater than the observed max. And then, you can take just take the tail area of that, convert it to a percentile, normal percentile on the z scale. And if that z of this p-value is greater than z alpha, you can reject. Or in other words, if the p-value itself is smaller than alpha 1, then you reject. Now, if you couldn't reject, then you compute an independent p-value just from the incremental data of the second stage. So you now compute the probability. So now this I2, the 2 is in brackets, which implies that it's just the incremental data from the second stage rather than the cumulative data. If I hadn't put a bracket around it, it would be the cumulative data from both stages. So the second stage p-value is similar, probably that the maximum of WI bracket 2 is greater than the maximum of the observed. And then you combine them. You combine these 2 z statistics with weights. Typically, these weights are proportional to sample size, but you can have any weights as long as the sum of squares of the weights is 1. And these weights have to be pre-specified. So then, this combined p-value should be greater than z alpha minus alpha 1. And so this is now the equivalent test to the group sequential, except that the main difference between the group sequential test and this test is the following, that the group sequential, if you ignore this Muller and Schaefer adjustment, uses the cumulative data. It sees what's the equivalent to getting a p-value based on all the data at one shot. Whereas the p-value combination test is saying, I'll calculate the p-value of the first stage separately, I'll calculate the p-value of the second stage separately, and then I'll combine them. And so given this difference, the question is, which is better? And so my rest of my talk is comparing these methods. So I have different comparisons. The first one is I've got 2 active doses and 1 control, And I'm going to choose a case where delta could go from 0 to 0.4 for the first dose, and also 0 to 0.4 for the second dose, and sigma squared is equal to 1. For this first example, I'll assume no early stopping and no sample size re-estimation. The only difference is that you either calculate the p-value cumulatively, or you calculate two independent p-values and combine them. And you don't need to worry about this. I've worked out analytically in this case what is the difference in power. The only thing that you need to see in this is that the two have very identical expressions. This you integrate over the first stage, and then you integrate over the second stage. But the difference is only in the limits of integration. Otherwise, the expressions are identical. In the group sequential, these are the limits of integration, and in the combo, they're a little more complicated. But the important thing is to look at the plot of the difference. So you see that in this first example, so the blue one is the group sequential, and the red one is the p-value combination. And you see that when the deltas are different, so here's delta equals, the delta 1 is 0 and delta 2 is 0.4, then there's about a 5% improvement in power. And similarly over here, when delta 1 is 0.4 and delta 2 is 0, there's about a 5% difference in power. The bottom plot is the difference in power, about 5%. And when the two deltas are the same, there's no difference in power. They're almost same. Now this was a case of only two doses and no early stopping and no sample size consolidation. So in summary, two treatments compared to a common control, you can get improvements of about 5%, but it depends on whether the two deltas are the same or the two deltas are different from each other. So then we went to a more realistic situation where we have three active doses to a common control, and we took values of delta 1 going from 0 to 0.3, and delta 2 going from 0 to 0.3 in groups of 0.5. And then we said, let's suppose that delta, since it's difficult to represent in 4 dimensions, we said let's fix delta 3 at 0.3, let's delta 1 vary from 0 to 0.3, and delta 2 vary from 0 to 0.3. And let's have a dose selection rule. We'll have two dose selection rules. One dose selection rule is drop at the end of the first stage. This is a very strict dose selection rule in the sense that you make it difficult to drop doses. You'll drop only if the observed delta is less than minus 0.3. And the other is a little more generous. You drop if the observed delta is less than 0.1. And then once you drop a dose, you reallocate the remaining to the arms that are going forward. And I did this I couldn't do this analytically. We did this with 10,000 simulations. And so you see now the results. Here's delta 1 going from 0 to 0.3. Here's delta 2 going from 0 to 0.3. And delta 3 is remaining at 0.3. And the selection rule is cut off at the first stage if the delta hat is less than minus 0.3. So you see that if the two deltas are the same, if all here at this end of this cube, all three deltas are the same, then there is no gain in power. This height is the gain in power of group sequential versus a p-value combination. And you can see that when there's complete heterogeneity of the deltas, that is delta 3 is 0.3, delta 1 is 0, and delta 2 is 0, then the gain in power is like 12%. You can get up to 12% more power with the group sequential method over the p-value combination method. And then it sort of steps down as the deltas become closer and closer to each other. The power gain is less and less. So it ranges from, from 0 to 12. Now, of course, this was a situation where we made it very difficult to drop losing doses. We said we want the losing doses only if a dose is a loser only if the delta hat is less than minus 0.3. So we also said let's try what happens if we make this easier to drop doses. And this is where the cutoff is minus 0.1. You drop doses if the delta hat is less than minus 0.1. That is to say, the control is better than the treatment by 0.1. And now you see the gain is somewhere around 8% at most. Again, it goes, but the same trend. As the deltas differ, you get more and more gain in power. And these are substantial gains. I mean, 8% gain in power is quite a substantial, would lead to quite a big change in sample size. So we see that in summary, we compared 3 treatments to a common control, and the dose selection and sample size re-estimation were done at stage 1. As before, I call it MAMS, it's actually both are MAMS. MAMS simply means multi-arm, multi-stage. I should say group sequential dominates over p-value combo. And the power gains increase with increasing heterogeneity. You can get up to 12% power gain with 3 active doses, and we'll get even more with 4 active doses, for instance, and a strict futility cutoff up to 9% gain in power with a more liberal futility cutoff. How much time do I have? 50 minutes. So that was the investigation that we did just with analytical and simulation methods. Then we also applied it to an actual trial, the Socrates for reduced ejection fraction trial. Well, this trial was we didn't participate in it. We just redesigned it to see what would have happened had we used these methods. It is very Verisiguat. I don't know how you pronounce this, but it's some treatment for reduced ejection fraction heart condition. And there were 3 doses, 3 active doses compared to placebo, and the endpoint was the change in this marker, NT-proBNP. This actual trial enrolled was underpowered. The reason it was they only took 65 patients per arm, and it was underpowered because they were going to they sort of assumed that these 3 doses would all be effective, and that the statistical analysis plan was to combine all the doses and test them against a common control, which was a big mistake, because as you can see, what happened was the first 2 doses were really not very good, and the 3rd dose was effective. But by pooling them like that, they diluted the effect, and then the trial failed. So what we figured is what if we had been involved from the beginning and had treated it as a regular multi-arm trial against a common control with an interim analysis to drop losing doses. And so we speculated that if we had designed it in that way from the beginning, we'd have needed 97 per arm under the assumption of a common delta of 0.187, which is what they had assumed in their design. Now, of course, the power will deteriorate if the deltas are not 0.187. So we said we will use a p-value we will use a two-stage design where we will drop arms which are not good and combine reallocate sample size to the remaining arms. And then this is the kind of result that you would have got. I've compared, I've taken different possible values of delta for the three arms. This is the complete homogeneous case, and this is the complete heterogeneous case. And then I've also put the null hypothesis, the global null, just to make sure that the type 1 error is controlled. And the first two columns are non-parametric tests, Bonferroni and Symes. The third one is the p-value combination test that we've been discussing, the max p-value from the two stages, the Dunnett p-value combined. So this is combining the two stages, and the last column is the group sequential, where you use the cumulative results. And you see differences sort of similar to what we had seen. Here the rule that I used for dropping arms was even more generous. If at an interim analysis the delta was less than 0, if the delta hat was less than 0, we would drop it. In this simulation, that's what I said. What would happen if I dropped all those arms where the delta was less than 0? So you wouldn't get as much, as strong a result as we got if you would have said, I want an even stricter rule, such as dropping doses if the delta is 1 standard deviation or away from 0, for instance. And you can see that there again the group sequential method dominates over all the others, and you get a gain of about 4%, 4 to 5% for the complete heterogeneous case, and you get no benefit for the homogeneous case.
Sorry, can you just go on the mic? It's difficult to hear you at that one.
Yeah, so I'm saying, thank you. You get no benefit in the heterogeneous in the homogeneous case for Dunnett versus group sequential, that is p-value combination versus group sequential, and you get about 4% improvement in power for the heterogeneous situation. So, in conclusion, the group sequential approach with closed testing and controlling the type 1 error by adaptive methods dominates over the p-value combination, and it dominates with power gains that increase with increasing heterogeneity of the deltas, and the power gains also increase with increasing conservatism of dropping the doses. The more difficult you make it to drop doses at the interim, the more power you'll have with the group sequential. The Bonferroni and Symes are not really competitive with the Dunnett or the MAMS. So you might think, well, Dunnett and MAMS require assumptions of normality, so naturally they have more power. But we also adjusted for that. We adjusted the nominal alpha to guarantee control of type 1 error. I want to say that there is also such a thing as an adaptive Dunnett test, which was published by Koenig and others, and it's closely related to the work that I've done, but we've approached it from the group sequential framework and provided more detailed calculations for the gain in power. And we have generalized it in East for K stages. All right, thank you.